In the quiet dark between stars, entire worlds begin as cold dust and faint light. Tonight's journey follows star formation step by step. From drifting molecular clouds to collapse and protostars to glowing disks where planet-building material takes shape, every chapter moves slowly, every image lingers, every idea lands gently so the mind can rest while the universe keeps unfolding. If this kind of calm science storytelling belongs in the night tap, like to support the channel, subscribe to Space Dreams Documentary for more long-form cosmic documentaries, and turn on notifications so the next voyage arrives right on time. A molecular cloud can look like a missing piece of the sky. It is not empty. It is a crowded, cold mixture of gas and dust. In that region, darkness forms because light is absorbed and scattered by tiny solids. The first anchor arrives quickly. Stars form when parts of this cold cloud become dense enough to fall inward. The scene begins wide. A long swath of space holds a faint background of distant starlight. Across it, a shadowy veil stretches in uneven sheets. Filaments run through the veil like strands of kelp in a slow undersea current. Each strand has a soft edge. Each edge fades into the surrounding black by a gentle gradient. The cloud does not glow much. It mostly reveals itself by what it hides. At this distance, the eye would register a pattern of dimming. Some stars remain visible as weak points of light. Others vanish behind thicker lanes. Dust acts as a filter. Shorter light is blocked first. Redder light passes farther before it too is reduced. That simple sorting is an early key. It explains why the cloud appears carved into layers of shadow. It also hints at where mass is gathering. The cloud's cold is extreme. Gas there can sit at about 10 degrees above absolute zero. That is colder than the coldest Antarctic air by a wide margin. Cold matters because it lowers pressure. Lower pressure makes it easier for gravity to gain ground. In one part of the veil, a filament thickens. Its center darkens while its edges remain translucent. A faint mottling appears in the lane. It is not a smooth curtain. It is a textured medium with clumps and gaps. A payoff arrives in that texture. The clumps are not decorations. They are the earliest map of future collapse. The scale shifts without effort. A filament can stretch for several light years. Inside it, denser pockets can be separated by distances like gaps between storm clouds on Earth. Yet the building blocks within are far smaller. Dust grains are comparable to the finest smoke particles. They drift among gas molecules with vast empty space between collisions. The same region holds both a structure measured in light years and ingredients measured in microns. That mismatch in scale is part of the calm mystery. It is also part of the mechanism. Large shapes guide flows. Small grains set how heat moves. The filament is not still. Turbulence ripples through it. Turbulence here means chaotic motion across many sizes. It creates bends and kinks. It also creates sharp contrasts in density. A strand can split, then rejoin. A faint braid appears. The braid is visible as a pair of parallel dark lanes that nearly touch. Between them, a thinner channel lets more background light through. The physical detail is clear. There are boundaries. There are edges. There are layered shadows that indicate depth. A second visual anchor settles in. A broad sheet of cloud lies behind the filament like a dim backdrop. In front, the filament's spine is darker, as if a ridge stands closer. That depth is not truly known. It is inferred from how the darkness overlaps. This is where a gentle limit appears. The cloud's interior cannot be seen directly at visible wavelengths. Light from behind is removed. Light from within is weak. Only what escapes along thinner paths reaches open space. Any picture of the center is therefore indirect. It relies on silhouettes and gradients. It relies on how different colors of light fade at different rates. The exact three-dimensional shape is uncertain. A lane that looks narrow could be a thin thread. It could also be a broad sheet seen edge-on. The mind wants a single answer. The data allow several. Even so, a practical truth holds. Where extinction is strongest, material is thickest. Where the gradient steepens, density rises faster with depth. Those are reliable signposts. Another payoff arrives in the way the filament connects to its surroundings. A faint web of thinner strands feeds into the main lane. The web suggests flow. Gas does not need to move fast to matter. It only needs to drift for a long time. In that region, time itself becomes an ingredient. A motion that feels slow on any short clock can reshape a cloud over many thousands of years. The cloud does not need a push from outside. Its own internal motion can create compressions. Its own gravity can amplify them. The calm promise of the story is set here. In these cold shadows, a pathway exists from diffuse gas to a star. The pathway begins with gathering. Gathering begins with imbalance. The filament holds more mass along its spine than along its edges. That mass pulls inward. It pulls sideways toward the center of the strand. It also pulls along the strand toward any slightly denser knot. The strand becomes a conduit. That word can stay simple. It is a route where material is guided by gradients in pressure and gravity. The filament's shape is not just appearance. Shape changes how forces add up. A thin ridge concentrates pull toward its axis. A broader sheet spreads the pull over a larger area. The difference matters when deciding where a core can form. The cloud's dust also changes chemistry. Surfaces of grains provide places for atoms to meet and stick. Simple molecules can assemble there. Later, those molecules will influence cooling. Cooling influences collapse. A small chain of cause and effect is already present. Dust blocks light. Blocking keeps the cloud cold. Cold allows density to rise. Rising density increases shielding. Shielding keeps the cloud cold again. The loop is quiet. It is not dramatic. It is steady and self-reinforcing. Another visual anchor arrives at a finer scale. Within the filament, the darkness is not uniform. Small scallops and notches appear along the edge. They look like soft bites taken from shadow. They are signs of uneven thickness. They also hint at turbulence that folds the lane. A fold can place more material in the line of sight. That creates a darker notch. A gentle scale shift follows. A notch may span a distance comparable to the width of a giant planet's orbit. Yet it is only a ripple within a structure that spans light years. The cloud's hierarchy becomes clear. There are sheets, there are strands, there are knots. Each level can feed the next. The limit of observation returns stated softly. No single view reveals the full mass distribution. Darkness alone cannot tell distance. Brightness alone cannot tell temperature. Multiple clues must be combined and some ambiguity remains. Still, the early anchor stays firm. Star formation begins as a problem of cold material collecting in a hidden place. The collection is traced by shadows and by gradients. It is prepared by turbulence and shaped by dust. Near the end, the filament's spine deepens again. A subtle bulge appears where the lane thickens. It is not yet a core, it is the suggestion of one. The scene eases toward the next step. In that region, motion within the cloud turns uneven thickness into distinct knots. Those knots will be the first places where collapse becomes inevitable. A filament inside a molecular cloud can seem stable for a long time. It becomes a birthplace only when motion and cooling allow a knot to hold onto extra density. In that region, turbulence compresses gas into pockets, then releases most pockets again. The scene narrows to a single dark lane. Its edge is not smooth. It carries scalloped indentations and brighter pinholes where the background leaks through. Along the spine, a faint thickening appears. It is like a crease in fabric that deepens when the cloth is gently shaken. That crease is not a separate object yet. It is a concentration that lasts longer than the surrounding ripples. A small payoff arrives early. Collapse does not begin from perfect stillness. It begins from a noisy medium where one compression outlives the rest. The filament holds flowing gas. Some flow slides along the strand. Some flow moves sideways toward the center. Where two streams converge, density rises. Where density rises, cooling becomes more effective because collisions increase. The gas can shed heat through radiation from simple molecules. Cooling matters because it prevents pressure from pushing back too strongly. A single concept can be kept plain. The core is a compact, dense region inside the cloud. That is the seed that can later collapse into a protostar. The core begins as a subtle gradient. The outer layers remain faint and translucent. The inner region becomes darker and more opaque. A visual anchor settles in. The core appears as a teardrop-shaped shadow embedded in the filament. Its long axis aligns with the strand. Its head is slightly rounder. Its tail fades into the lane. The boundary is not a hard edge. It is a smooth darkening that steepens near the center. Another payoff appears within that boundary. The steepness of the gradient is a clue. It suggests that material is not merely piled evenly. It is becoming centrally concentrated. Turbulence keeps working around it. The filament ripples, small eddies form. Thin side filaments feed into the main lane like tributaries joining a river. At the junction, the teardrop shadow sits slightly offset from the spine. The offset matters. It shows that convergence points can be lopsided. Gravity does not require symmetry to operate. It only requires extra mass in one place. A number enters softly. The core's densest region can reach about 100,000 particles in a cubic centimetre. That is still far thinner than air on Earth, yet it is an enormous increase for interstellar space. The comparison is immediate. It is like mist that remains mist but thickens from barely there to visibly present. This is a scale shift in disguise. Interstellar matter stays rarefied even while becoming dense enough to change its own future. The core begins to decouple from its surroundings. That does not mean it stops interacting. It means its internal gravity becomes more important than the random pushes of turbulence. Another visual anchor appears. Around the teardrop shadow, the filament shows faint striations, parallel streaks that suggest ordered motion. Some streaks curve around the core like gentle streamlines. They indicate that gas is being guided. The main analogy remains steady. The filament behaves like fabric under slow shaking. Most wrinkles appear and vanish. One crease deepens because the cloth gathers there. Another payoff arrives in that difference. The long-lived crease is a sign of threshold behavior. Below a certain density, compression relaxes. Above it, self-gravity can preserve the compression and increase it. The core also changes the light that passes through. Scattered light from surrounding dust creates a faint glow around the edges. The center remains darker. This creates a rim of soft brightness. It is not a sharp ring. It is a halo that marks where the column of dust becomes thin enough to let some light through. The physical detail is clear. There are layers. There is a gradient. There is a rim that traces thickness. The limit of observation is unavoidable here. The core's depth cannot be measured directly from its silhouette alone. A darker center could mean higher density. It could also mean a longer path length through modest density. Even temperature variations can change how dust emits and absorbs. Any three-dimensional model is therefore uncertain without additional clues. The uncertainty is specific. The line of sight compresses structure into a flat image. The true shape can be a flattened sheet, a cylinder, or a rounded clump. Still, the trend is reliable. A steepening gradient signals increasing concentration. The core's chemistry continues to evolve. Molecules that cool efficiently become more abundant in the cold interior. Dust surfaces collect icy coatings. Those coatings can trap heat less effectively. That allows the interior to remain cold. The loop tightens again. Cold enables density. Density increases shielding. Shielding preserves cold. Another scale shift arrives. A core can span a region comparable to a few times the distance between the Sun and its farthest planet. Yet it forms within a filament that stretches for light years. In time, the core's inner region can change in a period of about 100,000 years. That time scale is long for any short clock. It is brief compared with the life of a mature star. This is another payoff. Star birth is slow in moments. It is swift in cosmic history. Near the end, the teardrop shadow becomes slightly more compact. The rim glow narrows, the surrounding striations align more tightly toward the center. The filament still moves. The core now persists through that motion. The next step comes gently. In that region, gravity begins to turn persistence into inward drift. The shape of the core will start to matter more than the shape of the filament. A dense core can seem quiet from the outside. Inside, gravity begins a slow inward drift that turns a stable pocket into a collapsing one. At this distance, the change is first seen as a tightening gradient, not as motion. The scene holds the same core as before, yet the edges look subtly different. The teardrop shadow is more compact. Its rim glow is thinner. The outer envelope remains faint and soft, while the center becomes darker with a steeper fade. A gentle physical cue appears. The boundary where translucence turns to opacity moves outward a little. That suggests more material now sits along the line of sight. The core is still cold. Cold does not mean inactive. It means pressure support is limited. Gravity can then guide gas inward. The inward motion does not happen like a fall. It resembles a slow sag of material toward a low point. A new visual anchor arrives. A set of curved streamlines appears around the core, traced by faint dust brightness. They arc inward like threads pulled toward the eye of a whirlpool. The arc is not a perfect spiral. It is asymmetrical. One side is thicker, one side is slightly brighter. That asymmetry is not a flaw. It is the natural outcome of a core forming inside a turbulent filament. A payoff arrives in the shape. Collapse can begin without symmetry. It only needs a net inward pull that wins over random motions. One concept can be named briefly, then softened. Free fall is collapse driven mainly by gravity. It means the inward speed rises as the density rises. The phrase stays simple. The core does not instantly reach free fall everywhere. The outer layers lag. The center accelerates first. This creates a layered structure. A slow outer envelope feeds a faster inner region. The physical detail is concrete. The density profile becomes layered with a shallow slope outside and a steep slope near the middle. In that region, gas molecules collide more often. Collisions allow heat to be radiated away. That cooling keeps temperature from rising too quickly. Cooling is not a side note. It is one reason collapse can continue rather than stall. A single number enters with care. The central region can reach a density about 1 million particles in a cubic centimetre. That is like fog thickening until visibility drops, yet still far thinner than air. The comparison settles the scale. Density in space can rise by huge factors and remain tenuous by everyday standards. Another payoff comes from that contrast. Collapse is not about becoming solid. It is about becoming concentrated enough for gravity to keep winning. The scene shifts inward. The rim glow becomes more evident as a thin shell. It outlines where scattered light escapes. The center remains a deeper shadow. Light behaves as a biased messenger. It reports surfaces and edges better than interiors. The darkest point is not necessarily the densest point. It can be the longest path through dust. This is a gentle limit of observation. The line of sight compresses depth into darkness. The core's true three-dimensional shape remains ambiguous. A rounded clump and an edge on sheet can produce similar silhouettes. Even when longer wavelength light is used, resolution can be limited. Fine structure can be blurred into one smooth gradient. Models must assume temperature and dust properties. Those assumptions can shift inferred mass by a large factor. The limit is specific. The uncertainty comes from projection and from limited resolution, not from a lack of physical principles. Even so, the direction of change is clear. The gradient steepens, the rim narrows, the core is tightening. Another visual anchor appears about 150 words later. A faint hourglass-shaped dimming forms across the core's outskirts. It is not an outflow yet. It is a shadow of geometry. Slight flattening begins as material prefers a plane set by rotation. Rotation is the second concept. It does not need large speed to matter. Even a gentle spin becomes important when a region shrinks. As the radius decreases, conservation of angular momentum increases rotation. The core's motion changes character. Infall becomes slightly curved. Gas no longer heads straight inward. It slides inward along arcs. The main analogy is new and kept stable. The collapsing core resembles syrup sinking through a funnel. It moves slowly. It thickens toward the center. It flows along curved walls rather than dropping as a rigid block. The analogy stays gentle. It also helps interpret the hourglass dimming. The funnel narrows. Material gathers and begins to define a preferred direction. Another payoff arrives. Rotation does not stop collapse. It redirects it. It sets the stage for a disk later. The disk is not present yet. The seed of it is present as flattening and curved streamlines. The scale shift returns in time. The inward drift can unfold over about 10,000 years. That span is long compared with the flicker of turbulence. It is short compared with the lifetime of the star that will form. The core changes slowly. It changes decisively. The outer envelope feeds the center. The center grows denser. As density rises, the core becomes more opaque to its own cooling radiation. This introduces a subtle threshold. Cooling is efficient at first. Later radiation struggles to escape from the densest interior. Temperature then begins to rise. The rise is still modest at this stage, yet it alters pressure. Another payoff arrives. Collapse is a race between gravity and the ability to shed heat. When heat cannot leave easily, collapse changes style. It becomes more centrally concentrated. It prepares a hidden warm kernel. The limit of intuition appears softly here. It is tempting to picture a single moment when collapse starts. In reality, there is a gradient of onset. Some layers are still supported. Some layers are already moving inward. There is no clean boundary in time, only a growing region where gravity dominates. The scene holds the core again as a whole. The rim glow is now a finer outline. The teardrop is rounder at the head. Its tail is less diffuse. The filament around it still shows ripples, but the core's center remains steady. The next transition can arrive without suspense. In that region, the inward drift continues until the center becomes opaque and warm. The next step will be a cocooned object forming at the very middle, hidden by dust. A collapsing core becomes most interesting when its center turns hidden. The center grows opaque, then warms, and the first cocooned object forms inside dust. In that region, the outer layers still look calm, while the interior changes faster than the surface suggests. The scene begins with a core that no longer looks like a simple teardrop. Its outline rounds out. The rim glow becomes a thin, uneven shell. The shell is brighter on one side, dimmer on the other. A shallow lane of darkness crosses the core's face. It is not a gap. It is a thicker band of dust seen edge-on. The physical details stay slow and clear. There is a layered gradient from faint edge to dark center. There is a subtle boundary where the silhouette becomes almost fully opaque. There is a soft sheen of scattered light at the periphery. At this distance, the core's interior cannot be seen at visible wavelengths. Light behaves as a surface tracer. It marks where dust is thin enough to leak glow. It fails where dust becomes too thick. A payoff arrives early. Hiding is not an inconvenience. It is a sign that collapse has crossed into a new regime. When the center is shielded, it can cool differently. It can also begin to heat without immediately losing that heat outward. The second concept is simple and short. Opacity is how strongly material blocks light. In the core's center, opacity rises as density rises. Dust grains present more surface area. Gas becomes thick enough that radiation is trapped longer. Heat does not vanish quickly. Heat accumulates. That accumulation is gradual. It is also decisive. A new visual anchor settles in. A small bright patch appears offset from the darkest point. It is not a star. It is a faint glow in longer wavelength light leaking from a warmer inner region. Around it, the silhouette remains dark. The glow looks like a candle behind frosted glass, yet no flame exists. It is only heat and dust interaction. The glow has a smooth profile. It fades outward without sharp edges. Another payoff arrives in that profile. The warm region forms before a true star exists. It is created by compression. Gravity squeezes gas. Squeezing raises temperature. Temperature rise increases emission. Some emission escapes along thinner paths. Most remains trapped. The object is now a protostar. The definition can be brief. A protostar is a forming star not yet powered by fusion. The language returns to plain imagery. It is a warm kernel inside a cold blanket. It gathers mass. It brightens in ways that depend on the blanket's thickness. The blanket is the infalling envelope. It continues to feed the center. Material slides inward. It does not arrive in a straight line. Rotation still curves the infall. The curved streamlines tighten. Near the center, flattening becomes clearer. The earlier hourglass dimming becomes more definite. A narrow waist appears. Above and below the envelope look slightly more transparent. This creates a faint bipolar cavity shape. It is not fully carved. It is a hint of preferred directions where light and gas escape more easily. The main analogy is new and held steady. The forming protostar resembles a pearl forming inside an oyster. The shell is the envelope. The pearl is the warm kernel. Layers build slowly. The outer layers remain rough and irregular. The inner kernel becomes smoother and more defined as it grows. The analogy stays gentle and physical. It also clarifies why the center can be warmer while the outside stays cold. Another visual anchor arrives about 150 words later. A thin shadow lane cuts across the glowing region like a narrow band. It suggests a flattened structure starting to appear. It is not yet a full disk. It is a dense mid-plane where dust is concentrated. The lane has a soft edge. It is darkest at the center. It fades outward. The lane creates an impression of depth. The glow above and below is slightly brighter because the path through dust is shorter there. This is a quiet geometric payoff. A flattened structure can announce itself by how it dims light in a narrow stripe. A number enters with care and calm. The inner warm region can rise to about 100 Kelvin. That is like a warm room in a cold world. The comparison is immediate and simple. The envelope around it can remain only a few tens of Kelvin. This contrast matters. It changes which molecules stay frozen on dust and which return to gas. It changes cooling and chemistry. It changes how the next stages unfold. A scale shift follows. The warm kernel can be only a few times the distance between the Sun and the farthest planet across yet. It sits inside an envelope thousands of times larger. Time shifts too. The inner region can evolve noticeably in about 1,000 years. The outer envelope changes over far longer spans. The system therefore carries two clocks. One ticks quickly at the center. One ticks slowly at the edges. Another payoff arrives from that dual clock. The outside can look almost unchanged while the inside reorganizes. This is why early stages can be easy to miss when only silhouettes are seen. The limit of observation becomes sharper here and stays specific. The warm glow can be measured only where radiation escapes. Dust blocks the densest lines of sight. Even at longer wavelengths, emission can saturate. It can hide the highest densities behind a smooth brightness profile. Resolution can blur a small inner structure into one pixel-sized blob. Any inferred mass and temperature depend on assumed dust properties. If grains are larger or coated with ice, opacity changes. Models must choose a dust recipe. Different recipes can yield different central temperatures from the same brightness. The limit is not ignorance, it is degeneracy in interpretation. Several combinations of temperature and opacity can match the same observed glow. Even with that uncertainty, the geometry provides stable clues. The shadow lane signals flattening. The bipolar transparency hints at preferred escape routes. The rim shell still traces the envelope boundary. The story remains coherent. Collapse has produced a hidden warm kernel. Rotation has begun to gather material toward a plane. The envelope continues to feed inward. Near the end, the glow becomes slightly more elongated along the cavity direction. The shadow lane looks a touch sharper. The next transition arrives softly. In that region, a true disk will emerge from this flattening. The flow of mass will become channeled through that disk before it can reach the center. A warm protostar remains hidden, yet its surroundings begin to flatten into a clear shape. A disk forms because rotation channels in falling material into a thin plane. In that region, geometry becomes a guide that turns drifting gas into ordered flow. The scene opens close to the cocooned glow. The faint brightness is still wrapped in dust. Across it, a shadow lane now looks broader and more deliberate. It stretches outward on both sides like a calm horizon line. Above and below the envelope is slightly brighter. This contrast is not decoration. It is the signature of a flattened structure embedded in a thicker cloud. The physical details hold steady. The lane has a darker midline. Its edges are feathered. The glow above it fades with a smooth gradient. The glow below mirrors it, yet with small asymmetries. Infall continues. Gas and dust slide inward along curved paths. Near the center, those paths meet a limit. Rotation prevents straight inward collapse for some material. Instead, material settles into orbit. Orbit here can stay plane. It is a path where inward pull is balanced by sideways motion. The disk is born from that balance. A payoff arrives early. The disk is not an extra feature. It is the necessary bridge between a cloud and a star. Without it, most rotating material would have no simple route to the center. A new visual anchor settles in. The disk appears as a thin, dark plate. It is surrounded by a faint flared haze that rises above the midplane. The haze is dust lifted by thermal motion and by gentle stirring. The plate itself is denser and colder. It blocks more light. The flared edges create a soft V shape in brightness. Near the midline, the shadow is deepest. Farther out, the disk becomes translucent. The far edge shows a thin, bright rim where scattered light grazes the surface. That rim is subtle. It is like the edge of a leaf lit from behind. The main analogy is new and stays consistent. The disk behaves like a record of soot spinning in still air. The soot settles into a thin layer. The layer keeps spinning because friction is low. The surface looks dark and smooth, yet small ripples travel through it. The analogy clarifies two things at once. Settling creates a plane. Rotation preserves motion within that plane. Another payoff arrives in how the disk feeds the center. Material cannot fall straight in. It must lose angular momentum. That loss happens through internal stresses and through magnetic coupling to the gas. The details can remain gentle. Different rings of the disk orbit at different speeds. Inner regions move faster. Outer regions move slower. This shear drags on the material like slow rubbing between layers. It transports angular momentum outward. That allows some mass to drift inward. The disk therefore acts like a conveyor that can move mass and redistribute motion. A number enters with care. A young disk can extend to about 100 astronomical units. That is like a circle with a radius a bit larger than the farthest planet's orbit. The comparison settles scale without strain. Inside that span, the thickness is small compared with its width. The disk is thin in a vertical sense. It is wide in a radial sense. This is a scale shift in shape. A structure can be enormous in diameter and still be a narrow sheet. Another visual anchor appears about 150 words later. The disk surface shows faint banding. Some bands are brighter, some are darker. They are not sharp rings yet. They are gentle zones where dust density changes. A shallow spiral arc can also appear as a slight twist in the brightness pattern. The arc is not a rigid arm. It is a wave in a rotating medium. The physical detail is specific. There are gradients along the radius. There are layers above and below the midplane. There is a shadow cast by the dense midplane onto the surrounding envelope. That shadow can project outward like a dark wedge. Light behaves as a sculptor here. It turns thickness into shadow. It turns flare into glow. Another payoff arrives from that shadow. A disk can be detected not only by its own emission. It can also be detected by the pattern it imprints on nearby dust. The disk changes how light escapes the cocoon. It creates preferred bright directions above and below. It creates preferred dark directions along the midplane. The limit of observation becomes clear and specific. The disk's mass is hard to know directly. Dust emission traces temperature and opacity, not mass alone. If dust grains are larger, the same brightness can come from less mass. If the disk is optically thick, the interior cannot be seen. Only a photosurface layer is visible. Resolution can blur a sharp inner edge into a smooth gradient. The inferred radius can depend on sensitivity and on wavelength. Even velocity patterns can be ambiguous if viewed nearly face-on. The limit is therefore about degeneracy and orientation. Several disk structures can produce similar brightness maps. Still, one robust fact remains. A flat rotating reservoir has formed. It now controls the supply of material. Another payoff arrives in time. The disk can persist for millions of years. That span is long compared with the rapid tightening of the core. It is brief compared with the lifetime of a mature star. The system shifts from a fast collapse phase to a slower rearrangement phase. The disk becomes the stage where later assembly occurs. It is also the stage where the central object continues to grow. Accretion proceeds in bursts and lulls. The disk's inner rim can warm and puff slightly. The outer disk remains cold and thin. The vertical gradient stays gentle. Warmth near the center lifts dust into a thicker atmosphere. Cold farther out lets dust settle. This creates a layered look. The midplane is dense and dark. Above it, a lighter veil catches and scatters radiation. The analogy of soot remains useful. A thin layer can hide most of its mass in the darkest part. Only the surface reveals itself. Near the end, the banding becomes a touch clearer. The inner region looks smoother. The outer region looks more textured. The next transition arrives softly. In that region, the disk begins to organize its material into zones. Temperature and chemistry will set boundaries. Those boundaries will later guide where solids can survive and accumulate. A disk can look smooth until temperature draws invisible borders across it. Those borders decide where certain materials can stay solid and where they must become gas. In that region, the disk becomes a landscape of zones rather than a uniform sheet. The scene begins along the disk's surface. The thin, dark midplane still divides faint glow above and below, yet the brightness now changes with radius in a more deliberate way. Near the center, the haze above the midplane is thicker and softer. Farther out, the haze becomes thinner and clearer. The disk's edge shows a faint wide rim of scattered light. The rim is not sharp. It is a gentle fading where material becomes more diffuse. A physical detail stands out. A narrow band of slightly enhanced brightness runs around the disk at one distance from the center. It looks like a soft ring, not a crisp gap. Its inner side is warmer and brighter. Its outer side is cooler and dimmer. The ring is a boundary in temperature. It is also a boundary in chemistry. A simple concept can be named briefly. A snowline is the distance where a substance changes between ice and vapor. The language returns to imagery. It is like a shoreline in a cold world. Inside the shoreline, ice cannot persist. Outside it, ice can coat grains and remain. The disk holds several such shorelines for different materials. The most influential one is water. A payoff arrives early. The water snowline changes how much solid material is available. Outside it, ice adds mass to grains. Grains become stickier and heavier. Inside it, grains are drier and often less massive. The zone outside the boundary therefore becomes a favoured place for building solids. The main visual anchor settles in. The disk shows a dim inner region and a brighter, slightly puffed band at the water boundary. The band is like a pale bracelet wrapped around a darker plate. Its glow is not from jewellery. It is from dust temperature and from the way ice-coated grains interact with radiation. The bracelet is not perfectly even. It has gentle mottling. Some segments are brighter, some are fainter. That mottling suggests that the boundary is not a single razor-thin circle. It is a region that can shift with time and with local density. The main analogy is new and stays consistent. The snow line resembles a frost line on a window at dawn. The glass is colder at the edges and warmer near the centre. Frost forms where temperature falls below a threshold. The frost boundary makes a visible curve. It can move as conditions change. This analogy keeps the physics calm. It also explains why the boundary can be a zone rather than a line. Another payoff arrives in motion. The disk does not hold static temperature. Material drifts inward. Accretion releases heat. The central object brightens gradually. That heating can push the boundary outward. Cooling can pull it inward. The frost line on a window shifts with a small change in warmth. The same idea applies here, yet across a vast distance. A number enters with care. The water snow line can sit at about 3 astronomical units in many young systems. That is like the distance from the Sun to the region of the asteroid belt. The comparison is immediate. It places the boundary in a familiar scale without using any instruments or people. The scale shift is gentle. A boundary that governs microscopic ice on dust grains is set by a distance measured in astronomical units. Microphysics writes rules across a wide disk. Another visual anchor appears about 150 words later. The disk surface shows a subtle change in texture across the bracelet. Inside, the glow is smoother and more uniform. Outside, the glow is speckled as if dust clumps are more prominent. This speckling is not decoration. Ice-coated grains can grow faster. Faster growth can produce larger particles that settle closer to the midplane. Settling can change the surface brightness. It can also change how the disk scatters light at shallow angles. Another payoff arrives. Temperature boundaries can create traffic jams of solids. When grains drift inward, they can lose ice at the boundary. Losing ice reduces size and stickiness. That can slow further growth. Some material can pile up just outside the boundary where ice remains. The boundary becomes not only a chemical switch, it becomes a place where mass can concentrate. The disk's physical structure responds. A slightly higher surface density can create a small bump. That bump can create a gentle pressure maximum. Pressure maxima can trap drifting particles. This can be said without heavy equations. A pressure maximum is a region where gas pressure is locally higher than nearby. It acts like a shallow basin for drifting solids. The payoff is immediate. Solids drift inward until they reach a basin. Then they linger long enough and growth becomes more likely. The limit of observation appears and stays specific. A brightness bracelet does not directly reveal composition. A bright ring can arise from temperature alone. It can also arise from changes in grain size and scattering. Without resolving the disk in multiple wavelengths, the cause remains ambiguous. Resolution can blur a narrow boundary into a broad band. Orientation can hide it if the disk is face-on. Even when a ring is seen, its exact radius depends on model choices for dust opacity. The limit is therefore a mixture of degeneracy and resolution. More than one underlying structure can paint the same brightness pattern. Even with that uncertainty, the concept holds. Temperature creates distinct zones. Zones change the supply and behavior of solids. Another scale shift arrives in time. The boundary can move over thousands of years as accretion varies. A grain crossing the boundary changes phase in a much shorter interval. The disk therefore holds fast transitions at the microscopic scale and slow migration at the orbital scale. The story remains quiet. The disk is becoming structured by gradients. It is becoming a map of where certain materials can persist. Near the end, the bracelet band looks slightly sharper. The inner smoothness looks more uniform. The outer speckling looks a touch stronger. The next transition is gentle. In that region, grains begin to collide and stick in the zones where solids are most abundant. The disk will start to turn dust into larger pieces that settle toward the midplane. A disk begins to build planets the moment dust starts behaving differently from gas. Growth starts when tiny grains collide and stick, then drift into a thin layer near the midplane. In that region, the disk quietly sorts its solids by size and by height. The scene opens on the disk, seen slightly from the side. The midplane is a dark stripe. Above it, a pale veil glows faintly. Below it, a mirrored veil fades into the surrounding darkness. The earlier temperature bracelet is now less prominent. In its place, a new structure appears. A thin, darker line runs along the very centre of the stripe. It is narrower than the overall mid-plane shadow. It suggests that solids are settling into an even thinner sheet. The physical detail is clear. There are layers. There is a sharpest darkness at the midline. There is a gentler gradient upward where dust density drops. At this distance, motion is not seen as moving dots. Motion is inferred from how structure changes. The first payoff arrives early. Dust does not remain evenly mixed. It sinks toward the mid-plane because gravity pulls it down and gas drag lets it lose vertical motion. Gas resists that settling. It stirs and puffs the dust upward. The balance produces a dusty atmosphere and a denser floor. A simple concept can be named briefly. Settling is the drift of solids toward the disk mid-plane. The language returns to imagery. It is like fine powder in still water. The powder slowly descends. A thin layer forms at the bottom. The water above stays hazy for a while, then clears. The analogy stays calm and physical. It also clarifies why a thin dark line can emerge. The powder layer becomes a preferred place for collisions. In the disk, collisions drive growth. Grain meets grain. Contact can be gentle. When surfaces are coated with ices or organic, sticking becomes easier. When surfaces are bare and fast collisions can bounce or fragment. Even so, the net trend can be upward in size. Dust becomes aggregates. Aggregates become pebbles. The scale shift arrives without strain. A grain begins smaller than a speck of smoke. Over time, clumps reach sizes comparable to sand, then gravel. The disk is vast. The growth is local. The path from micron to pebble is the first bridge from invisible to tangible. A new visual anchor settles in. Along the mid-plane, faint brightness bands appear like shallow ripples in a long dark ribbon. These are not gaps yet. They are density variations. Some zones are slightly denser and therefore darker. Other zones are slightly thinner and therefore brighter. The ripples drift slowly around the central object as the disk rotates. The disk's shear stretches any clump into an arc. That stretching is a physical detail. The arcs are subtle. They show that rotation turns local changes into long patterns. Another payoff arrives. Growth is faster where solids linger. Solids linger where turbulence is mild and where pressure gradients slow inward drift. The mid-plane layer becomes both a meeting place and a trap. Gas still flows above it. Gas still exerts drag. That drag causes drift. Pebble feels a headwind because gas orbits slightly slower than a solid would in a pure gravitational field. The pebble loses angular momentum and spirals inward. The concept can stay plane. Drift is the slow inward migration of solids due to gas drag. The analogy remains unique and gentle. Drift resembles a leaf sliding toward a drain in a slowly rotating basin. The water's motion is not a strong current. It is a subtle pull that persists. The leaf moves because small forces act for a long time. In the disk, the force is drag. The persistence is orbital repetition. Another payoff arrives in the consequence. Drift creates a deadline. If solids grow slowly, they move inward before they become large enough to resist drag. If solids grow quickly, they can remain longer in the zone where growth continues. This tension shapes the entire planet-building story. A number enters with care. Meter-sized objects can be especially vulnerable to rapid inward drift. That is about the height of a door. The comparison lands softly. It shows that the dangerous size is not microscopic. It is oddly familiar. It also shows why growth must skip or bypass certain sizes through clumping or concentration. Another visual anchor appears about 150 words later. The mid-plane layer now looks slightly corrugated. Tiny vertical undulations appear like soft waves. These undulations suggest turbulence near the mid-plane. Turbulence stirs. It can break fragile clumps. It can also bring particles together. The balance depends on collision speeds. In a calm disk, relative speeds can remain low enough for sticking. In a more stirred disk, fragmentation becomes common. The limit of intuition appears here and stays specific. It is tempting to imagine that sticking always wins. Laboratory and modelling results show that many collisions bounce, some shatter. Growth can stall at certain sizes. The exact sticking efficiency depends on grain composition porosity and relative speed. Those details are not directly measurable from a distant brightness map. Even if a thin mid-plane line is seen, the distribution of sizes within it can be uncertain. Larger grains emit and scatter differently. A disk with many big grains can look faint at some wavelengths. A disk with many small grains can look bright. Without multi-wavelength resolution, size and mass can be confused. The limit is therefore a degeneracy between grain size and dust mass, combined with limited resolution of the thinnest layer. Even so, the geometry keeps a reliable clue. A thinner central darkness suggests that solids have concentrated downward. Concentration makes collective effect possible. When enough solids gather their mutual gravity and their feedback on gas can create dense filaments inside the midplane. The story stays calm. The midplane becomes a quiet workshop. The air above is a dusty atmosphere. The floor below is a denser sheet. Another payoff arrives in scale. A dense sheet only a small fraction of the disk's thickness can contain much of the solid mass. This is how a wide disk can hide most of its building material in a narrow vertical layer. Time shifts gently. The growth from grains to pebbles can occur over thousands of years in favourable regions. The disk itself persists far longer. Many opportunities repeat as orbits cycle. Near the end, the ripples along the midplane appear slightly more contrasted. The central thin line looks darker and more continuous. The next transition arrives softly. In that region, solids begin to concentrate strongly enough that gravity can assist. The first durable seeds will form when clumps become self-held rather than just temporarily gathered. A thin dust layer can suddenly produce solid seeds when clumps become self-held. The first planetesimals form when dense swarms collapse under their own gravity. In that region, a quiet threshold turns drifting pebbles into enduring bodies. The scene opens along the disk mid-plane where the central dark line is now pronounced. The dusty atmosphere above remains faint. The floor is darker and more structured. Instead of smooth ripples, the mid-plane shows short segments of enhanced darkness like beads spaced along a thread. Each bead is not a single object. It is a concentration of many solids in a small volume. Between beads, the mid-plane line is thinner and slightly brighter. The physical detail is clear. There are alternating dense and less dense patches. The edges of each patch are soft. The centre of each patch is darker. A gentle gradient marks where solids thin out. At this distance, light behaves as a tracer of surfaces and of shadow. The densest part can hide behind itself. Even so, the pattern reveals a new organisation. A payoff arrives early. Growth does not need every pebble to stick into a larger pebble. It can instead proceed by concentration first, then collapse. Concentration can occur because solids and gas interact. When enough pebbles drift together, they slow the gas locally. Slower gas reduces headwind. Reduced headwind allows more solids to remain. A feedback loop begins. The loop can be named briefly. Streaming instability is a clumping process of solids and gas. The definition stays short and calm. It is a tendency for drifting pebbles to gather into dense filaments. The language returns to imagery. It resembles sawdust in a gentle eddy. Individual grains swirl. Then a streak appears where many grains align and collect. The streak grows denser because the flow keeps feeding it. The analogy stays unique and physical. Another payoff arrives in what the streak accomplishes. It creates a local region where solid density can rival gas density. When that happens, self-gravity matters. The clump no longer relies on the gas to hold it together. It can begin to collapse as a collective. A visual anchor settles in. One bead along the midplane becomes a thicker knot. The knot casts a small elongated shadow that extends a short distance along the disk plane. The shadow has a darker core and a lighter penumbra. It indicates a three-dimensional concentration, not just a flat enhancement. Around the knot, faint arcs appear as the disk shear stretches nearby material. The knot resists being stretched. That resistance is an early sign of self-binding. A number enters with care. The collapse can produce bodies about 100 kilometers across. That is like the distance between two far-apart cities on Earth. The comparison settles scale and keeps it gentle. It also marks a leap. The disk moves from pebble sizes to mountain range-sized objects. This is a major step with a quiet feel. Another payoff arrives immediately. A body of that size is hard to erase by simple collisions with dust. It can survive. It can also pull on nearby material. It becomes a seed that can grow by accretion and by gravitational focusing. The scale shift continues. A 100-kilometer body is tiny compared with the disk's radius. Yet it is enormous compared with grains. The disk is a wide stage. The seed is a small actor. Still, the seed changes local dynamics. The midplane layer is thin. The seed is thick and compact. It becomes a point-like mass in a sheet. Another visual anchor appears about 150 words later. Several knots appear in a chain. The chain follows a slightly curved path that traces a pressure maximum. The knots are not evenly spaced. Some are larger, some are smaller. The midplane line now looks braided in places. A braid is created when two dense filaments run parallel and then merge. The physical detail is specific. There are filaments, there are knots, there are arcs shaped by shear, there are shadows shaped by thickness. The environment remains calm. Gas continues to flow around the concentrations. Fine dust still floats above like haze. The solids in the midplane become more decisive. The limit of observation appears and stays specific. A distant brightness map cannot directly reveal the presence of 100-kilometer bodies. Such bodies do not radiate strongly at the wavelengths that trace dust. They can be invisible. Their presence is inferred from patterns in surrounding dust and gas. Gaps or rings can suggest their influence, yet similar patterns can also be produced by pressure waves or temperature changes. Even when a clump is seen, its true density depends on assumptions about grain opacity. Resolution can smear a narrow filament into a broader band. Sensitivity limits can hide smaller knots. The limit is therefore twofold. The bodies themselves are hard to detect directly. The clumping filaments are hard to measure precisely because of opacity and resolution. Even so, the threshold idea remains robust. When solids reach high enough density, self-gravity can take over. Another payoff arrives in how quickly this step can occur. Once a dense filament forms, collapse can proceed rapidly on orbital timescales. That can mean hundreds of years in the inner disk and far longer in the outer disk. The disk carries multiple clocks. Clumping can be sudden locally. The global disk evolution remains slow. A gentle timescale shift follows. Millions of years can pass while the disk persists. Within that span, planetesimal formation can happen in brief episodes in favourable zones. The disk's midplane is not a single continuous factory. It is a patchwork of active regions and quiet regions. The analogy of sawdust in an eddy remains steady. Most grains drift and disperse. Some streaks become dense enough to collapse into pellets. The pellets remain even when the eddy changes. The story stays calm and sequential. Dust grows into pebbles. Pebbles concentrate into filaments. Filaments collapse into bodies. Those bodies are the first durable building blocks. Near the end, the chain of knots looks more numerous. The midplane line looks less smooth and more granular. The next transition arrives softly. In that region, collisions among these early bodies begin to shape their surfaces. Heating and melting can occur in impacts. Materials will sort and transform as growth continues. A newborn planetesimal carries the memory of impacts in its surface layers. Collisions heat, melt, and rearrange material, turning loose rubble into more complex textures. In that region, growth becomes a story of both assembly and transformation. The scene opens within the disk's mid-plane, where the earlier chain of dense knots has dispersed into a swarm. Individual bodies are not visible as points. Their presence is implied by the dust they stir and by the faint changes they imprint on nearby material. The midplane line looks slightly rougher than before. It has a granular quality, as if the darkness is made of many tiny shadows overlapping. Here and there a narrow wake appears. It is a thin streak of altered brightness that trails behind an unseen mass as it moves through fine dust. The physical details stay gentle and clear. There are wakes, there are streaks, there are small gradients where dust density changes across a narrow line. At this distance, light behaves as a soft tracer of disturbance. A payoff arrives early. Once solid seeds exist, the disk becomes a collision environment. The collisions are not constant chaos. They are spaced in time. They are guided by orbital motion and by gravitational focusing. Bodies pass near one another many times before a direct impact occurs. When an impact does occur, energy concentrates in a small region. That concentration can melt rock locally, even while the surrounding space remains cold. A simple concept can be named briefly. Differentiation is internal separation into layers by density. The language returns to imagery. It is like a shaken jar of mixed sand and metal filings. Over time, heavier pieces settle toward the center of the jar's pile. Lighter pieces remain higher. In a planetesimal, the driver is heat. Heat allows material to move. Once molten, denser metal can sink. Less dense silicate can rise. Another payoff arrives. Differentiation does not require a planet. It can begin in bodies far smaller provided enough heat is available. Heat can come from repeated impacts. It can also come from short-lived radioactive decay early in the disk's life. The details can remain calm. The key is that some bodies warm enough inside to allow flow. A new visual anchor settles in. A single larger planetesimal is imagined indirectly, not as an observed object but as a physical scene. Its surface is irregular. It has rounded ridges and shallow basins. One basin holds a dark glassy patch. The patch has a smooth sheen. Around it the ground is rougher, made of angular fragments. The patch marks an ancient melt pool from an impact. Its edge is a thin raised rim where material splashed and cooled. The rim is a concrete physical detail. It has a boundary. It has a thickness. It records motion. Another payoff arrives in that rim. Impacts do more than break bodies. They can weld fragments together by creating melt that later hardens. The body becomes stronger in some places and weaker in others. Its history becomes layered. Beneath the surface, heat migrates slowly. Pockets can remain warm after an impact. Warm pockets can allow metal to drip downward through cracks. That creates streaks and veins. Even when the overall body is cold, local pathways can exist. The main analogy is new and stays consistent. The planetesimal behaves like bread dough with raisins and syrup. A sudden press creates a warm pocket. Syrup flows into gaps. Raisins shift and settle. When the dough cools, the new arrangement is locked in. The analogy stays gentle and physical. It also captures the mix of solid fragments and molten flow without invoking any tools or people. A number enters with care. An impact speed of about 5 kilometers per second is common in young swarms. That is like crossing a continent in less than an hour. The comparison settles the energy scale without equations. It also clarifies why impacts can melt rock. Speed squared becomes heat when motion stops abruptly. Another payoff arrives. Even a modest-sized body can experience intense local heating because the stopping distance is short. The surface records it as glassy patches and splashed rims. The interior records it as veins and layers. A visual anchor appears about 150 words later. A broken planetesimal is imagined in cross-section. Its interior shows a darker central region and a lighter outer shell. The boundary between them is not perfectly smooth. It is lumpy and scalloped. That indicates incomplete separation. Some metal remains trapped in pockets. Some rock sinks in blobs. The gradient is visible as a change in texture rather than color alone. The center is denser and more compact. The outer shell is more fractured. This connects to a calm payoff. Differentiation can be partial. Many bodies never become fully layered. They carry a mixed interior that records a brief warm phase, then a long cooling. The scale shift arrives in time. A single impact happens in seconds. The cooling of a warmed interior can take thousands of years. Over that interval, the disk continues to evolve slowly around it. Orbits repeat. Dust drifts. New impacts occur. The body's surface becomes a palimpsest of scars and flows. The limit of observation appears and stays specific. None of these internal textures can be seen directly at the distances where disks are observed. A distant signal from dust emission does not reveal a glassy patch or a metal core. Even for larger bodies, reflectance and brightness depend on dust coatings and viewing geometry. The internal layering must be inferred from models and from the physics of heating and cooling. Those models depend on uncertain initial compositions and on uncertain impact histories. Two bodies of the same size can end up very different. One can be rubble and cold, another can have a compact core and a crust. The limit is therefore about hidden interiors and about unobservable histories. Even so, the overall consequence is stable. Early collisions change material properties. They create harder pieces and softer debris. They generate fine fragments that can be reaccreted. They also create a spectrum of strengths that affects later growth. Another payoff arrives in how debris behaves. Small fragments can damp relative speeds by gas drag. That can reduce collision violence in some regions. It can also feed growth by providing easily captured material. The disk becomes a feedback system of break and rebuild. Near the end, the imagined surface of the planetesimal shows a final detail. A thin layer of fine dust settles into a shallow basin. It softens the sharpness of older scars. The next transition arrives softly. In that region, some bodies begin to grow beyond the planetesimal stage. Gravity starts to dominate encounters. Orbits and migration will begin to reshape where growth is fastest. A growing body begins to reshape its neighborhood long before it becomes a planet. Gravity amplifies growth by pulling in more material than simple collisions would allow. In that region, the disk's calm patterns start to show the imprint of invisible masses. The scene opens on the disk midplane, now less like a uniform ribbon and more like a lightly sculpted surface. The earlier wakes and streaks appear more frequent. Some streaks curve into shallow arcs. They trace paths where dust density is slightly reduced. Nearby, thin ridges of brighter dust appear like banks along a river channel. The physical detail is clear. There are arcs, there are ridges, there are gradients across narrow bands. The arcs are not sharp cuts, they are soft depressions. Their edges fade into the surrounding haze. A payoff arrives early. When a body becomes massive enough, it focuses passing material. This increases the rate of encounters. The effect can be named briefly. Gravitational focusing is enhanced capture due to gravity bending paths. The language returns to imagery. It is like a slow-moving snowball rolling through loose snow. It does not only touch what lies directly in front, it draws nearby snow into its path. The snowball grows faster than a simple sweep would suggest. The analogy stays unique and gentle. It clarifies why growth can accelerate once a seed reaches a certain size. Another concept joins it and remains simple. Migration is the change of orbit due to interaction with the disk gas. The disk is not a passive background. Gas exerts torques. Those torques can shift orbits inward or outward. The direction depends on local gradients and on the body's mass. This can be said without formulas. A body exchanges angular momentum with spiral waves it excites in the gas. Those waves carry momentum away. The body's orbit adjusts. A visual anchor settles in. A shallow pair of spiral ripples appears in the dust layer. One ripple leads ahead of an unseen mass. Another trails behind. The ripples are faint. They are only slight variations in brightness, yet they trace a physical pattern. The disk is responding. The ripples create a gentle S shape when viewed from above. Along the ripples, dust looks slightly compressed. Between them, dust looks slightly rarefied. Another payoff arrives in the symmetry. A single mass can create both leading and trailing disturbances. The disk's response is wave-like, not carved like a cut. This matters because it separates early influences from later gap opening. At this stage, the disk remains largely continuous. It is being stirred and shaped, not emptied. A number enters with care. A body around the mass of the Moon can begin to excite strong spiral structure in nearby gas. That is like a mountain-sized boulder compared with surrounding sand. The comparison settles the idea of relative influence. The disk is vast, yet a moon mass object can still act as a sculptor of local patterns. This is a scale shift of authority. A single object far smaller than the disk can still impose structure across a wide region of gas. Another visual anchor appears about 150 words later. A narrow, dark lane begins to appear at a particular radius. It is not fully open. It is a partial gap, more like a depression in dust density. Its edges show slight brightening, as if dust has piled up into two low ridges. The inner ridge is smoother, the outer ridge is more mottled. This difference can arise because drift and pressure traps act differently on each side. Another payoff arrives. Partial gaps can be created by bodies that are not yet planets. The gap does not mean emptiness. It can mean redistribution. Gas can still cross. Dust can still leak through in small grains. Larger grains can be trapped more easily. The disk sorts sizes again now under the influence of a growing mass. The main analogy of the snowball remains steady. The body is the snowball. The disk is the snowfield. In some zones, the snowball carves a shallow trench while gathering snow at its edges. The trench is not a cut to the ground. It is displacement of loose material. Another payoff arrives in migration. As the body interacts with the disk, it can move. The trench pattern can therefore drift in radius over time. This movement can bring the growing body into new material reservoirs. It can also bring it into zones where temperature and ice content differ. Growth is not only about local supply, it is also about where the body travels. The limit of observation appears and stays specific. A spiral ripple or partial gap in dust does not uniquely identify a single body. Similar patterns can arise from purely hydrodynamic waves, from variations in disk viscosity, or from changes in illumination geometry. Even when a body is responsible, its mass cannot be read directly from the depth of a dust gap. Dust responds to gas and to grain size. A deep dust depression can occur with modest changes in gas if large grains are trapped. Conversely, a significant gas depression can look shallow in dust if small grains dominate. Resolution can smooth multiple narrow gaps into one broad one. Orientation can hide spiral patterns when viewed edge-on. The limit is therefore about degeneracy between mass dust size distribution and disk physics. Inference requires models. Models require assumptions. Still, the story remains stable. Growing bodies excite waves. Waves transport angular momentum. Transport changes orbits. Orbits change where growth occurs. A scale shift in time arrives. Migration can operate over tens of thousands of years in some disk regions. That is short compared with the disk lifetime. It is long compared with an impact. The disk becomes a slow-moving conveyor of orbits. Growth becomes a guided journey rather than a fixed location process. Another payoff arrives near the end. Migration can deliver icy material inward or carry rocky seeds outward. This mixing changes the composition of later planets. It also changes where water and organics can accumulate. The disk is not only building objects, it is blending reservoirs. The scene eases outward. The partial gap remains shallow. The spiral ripples remain faint. The disk still looks calm as a whole. Yet the imprint of hidden masses is now present. The next transition arrives softly. In that region, the disk will begin to lose gas over time. As gas thins, migration slows. The remaining solids will settle into more stable architectures. A disk begins to calm when its gas starts thinning away. As gas disperses, orbits become more stable, and solids stop drifting so easily. In that region, the architecture of a future planetary system starts to freeze into place. The scene opens on the same disk, now viewed with a wider field. The outer rim looks fainter. The dusty halo above the midplane is less puffed. The midplane itself remains a dark stripe, yet it is narrower and more sharply defined. A new physical detail appears. The surface brightness drops more steeply with radius, as if the disk has been gently erased from the outside inward. The edge is not a cliff. It is a smooth taper. The taper is a gradient that signals lower density at large distances. A payoff arrives early. Gas is the medium that drives much of the early rearrangement. When gas fades, the disk becomes less like a fluid and more like a collection of solids on Keplerian paths. The concept can remain simple. Photoevaporation is gas loss driven by high-energy light. The definition stays short. It is the heating of upper layers until gas escapes. The language returns to imagery. It is like mist lifting off a cold lake when sunlight warms the surface. The lake remains. The thin veil above it thins and drifts away. In the disk, the mist is the tenuous upper gas. The lake is the denser midplane where solids remain. The analogy stays unique and calm. Another payoff arrives in how dispersal reshapes pressure. When gas surface density decreases, pressure gradients weaken. Weak gradients reduce the headwind felt by solids. Reduced headwind slows drift. Pebbles and fragments linger longer where they are. Growth becomes more local. Migration of larger bodies also slows because torques depend on gas. The disk begins to settle into zones where change is slower. A new visual anchor settles in. The disk shows a broad, faint cavity in the inner region. It is not an empty hole. It is a reduced brightness region with a soft boundary. Just outside the boundary, a brighter ring of dust appears. The ring looks like a low ridge at the edge of a shallow basin. The ridge is smooth on the inside and slightly mottled on the outside. The physical details stay clear. There is a cavity. There is a ringed edge. There is a boundary that is sharper than the outer taper. The cavity can form when gas is cleared from the inside, while dust piles up at a pressure bump. Another payoff arrives. Clearing does not remove everything evenly. It can carve from above and inside first. That can leave solids trapped in rings. Rings become reservoirs. Reservoirs become staging grounds for final assembly. A number enters with care. Many disks lose most of their gas within about 5 million years. That is like the time it takes a mountain range to weather by only a small fraction. The comparison is gentle and sets the time scale. 5 million years is short for stars. It is long for any single collision. It is the interval that decides whether gas giants can gather thick envelopes. It also decides how far migration can proceed. Another visual anchor appears about 150 words later. The ring at the cavity edge shows faint substructure. Shallow gaps appear within it. They are not deep trenches. They are slight dips in brightness spaced along the ring like soft notches. These dips suggest that growing bodies are shepherding dust. The disk's remaining gas is too thin to smear these features away quickly. The ring therefore preserves the imprint of interactions. The main analogy of mist lifting remains steady. As the mist clears, the shoreline becomes visible. In this case, the shoreline is the cavity edge. It is where material collects because pressure and drift balance. Another payoff arrives in stability. A ring that persists can act as a long-lived trap for solids. This trap allows repeated gentle collisions. It also allows gravitational interactions among larger bodies to dominate without being constantly damped by gas. With less gas, eccentricities and inclinations can grow. Orbits can become more elliptical. Encounters can become more energetic. Yet the overall environment still remains sparse. Most of space is empty. The changes are subtle and slow. The limit of observation appears and stays specific. A dimming of gas cannot be seen directly in the same way as dust brightness. Gas emission lines can be faint and depend strongly on temperature and chemistry. A disk can appear dust poor while still containing gas. It can also appear gas poor because gas is too cold to excite emission. Dust rings can remain after gas has gone. That can confuse timing. Even the cavity can be ambiguous. A reduced brightness region can be caused by grain growth, not by clearing. Larger grains emit differently and can make an inner disk look faint. Resolution can also blend a narrow ring into a broad one. The limit is therefore about disentangling gas loss from dust evolution. Inference depends on models of grain size and gas heating. Still, the physical arc holds. Gas thins, drift slows, migration weakens, solids settle into rings and belts. Another payoff arrives in composition. As gas disperses, volatile transport changes. Ice can sublimate and recondense less efficiently. The distribution of water and organics becomes more fixed. Some regions become dry, others retain ices. This sets initial conditions for later atmospheres and oceans, though those details remain beyond the disk stage. A scale shift arrives in spatial perspective. The cavity edge and ring may sit at a few astronomical units. The outer taper extends tens or hundreds of astronomical units. The inner changes can occur quickly once clearing begins. The outer disk can linger as a faint halo of dust and gas for longer. The system carries multiple fading layers. Near the end, the ring looks sharper against the dimmer background. The outer disk looks more transparent. The next transition arrives softly. In that region, the remaining solids will undergo a longer phase of collisions and mergers. Without much gas to cushion them, the final shapes of planetary orbits will be decided by gravity among the bodies themselves. A young system settles when collisions shift from building to pruning. Orbits spread overlap and then simplify as bodies merge or are scattered away. In that region, order emerges from many slow interactions rather than from a single event. The scene opens on a disk that is now mostly dust and solids. The gas veil is faint. The mid-plane stripe is thinner and more sharply edged. The bright ring near the old cavity boundary still exists, yet it is less luminous. It looks like a chalky band on a dark surface. Within and beyond it, the dust brightness is mottled. Small dips and ridges appear like gentle waves frozen in place. The physical details remain clear. There are bands, there are notches, there are smooth gradients between denser and thinner zones. A payoff arrives early. When gas damping weakens, gravity among the bodies becomes the main sculptor. Small changes accumulate. Orbits can become slightly eccentric. Inclinations can thicken the swarm. Relative speeds rise. Some collisions become more erosive, others still merge. The net result is a filtering process that leaves fewer larger survivors. A simple concept can be named briefly. Dynamical friction is the calming effect of many small bodies on large ones. The definition stays short. It is the tendency for large bodies to lose random motion to a swarm. The language returns to imagery. It is like a heavy stone rolling through loose gravel. The gravel shifts and absorbs the stone's jolts. The stone's path becomes smoother even as the gravel is stirred. The analogy stays unique and gentle. Another payoff arrives. A system can calm even while it remains active. The larger bodies can circularize over time because the smaller debris acts as a brake. At the same time, the small debris is gradually consumed or scattered. This is a quiet trade. Calmness is purchased by using up the swarm. A visual anchor settles in. A belt of debris appears as a faint broad glow ring wider than the earlier pressure trap ring. Its inner edge is sharper, its outer edge is more diffuse. Within the belt, brightness is uneven with clumps and gaps that shift slowly. The belt is a reservoir of leftovers. It is also a record of ongoing collisions. Each collision releases dust that briefly brightens a patch before it spreads. The physical detail is specific. There are clumps shaped like arcs. There are sharp inner boundaries. There are soft outer tapers. Another payoff arrives in what the belt implies. Not all material becomes a planet. Some remains as a belt that persists for long intervals. That belt continues to grind down through collisions. Dust created there can drift inward and be removed. The belt therefore slowly fades, yet it can remain detectable for a long time. A number enters with care. The late stage of giant impacts among larger bodies can last about 100 million years. That is like the time between major shifts in continents on Earth. The comparison is gentle and sets the time scale. It also provides a scale shift. A single impact happens in moments. The sequence of impacts that shapes final planets stretches across deep time. During that interval, the system's architecture can change repeatedly, then settle. Another visual anchor appears about 150 words later. A large body passes near the debris belt and creates a narrow gap. The gap is not perfectly empty. It is a region of reduced brightness with two faint ridges at its edges. The ridges are slightly brighter because dust is shepherded into resonant paths. The gap's boundaries look like subtle grooves pressed into soft clay. The groove is narrow at first. Over time it widens as more material is cleared or redirected. The physical details stay calm. There is a groove. There are ridges. There are gradients that indicate partial clearing rather than a sharp cut. Another payoff arrives. A single body can impose structure without needing gas. Resonances can gather and remove material. Resonance here can stay plane. It is a repeating gravitational nudge that accumulates. A small nudge repeated at the right rhythm can redirect orbits. Some orbits become crowded. Some become unstable. The belt therefore becomes segmented. Segments can later resemble asteroid belts or Kuiper-like belts depending on distance. The limit of observation appears and stays specific. A dusty belt's brightness depends on ongoing collisions, not only on mass. A massive belt with few collisions can look faint. A light belt with frequent collisions can look bright. The clumps and gaps can also be transient. A bright arc can be a recent collision cloud that will disperse. A gap can be a temporary pattern from a passing wave of dust. Without tracking changes over time, cause can be ambiguous. Even the presence of a planet cannot be proven from dust structure alone. Several configurations can produce similar belts and gaps. Resolution can blur narrow gaps. Sensitivity can hide diffuse outer halos. The limit is therefore about interpreting patterns created by dust as indirect evidence of bodies. Indirect evidence can be strong, yet it is never a direct image of the builders. Another payoff arrives in composition. As collisions proceed, materials are redistributed. Some impacts vaporize volatiles locally. Some preserve ices in cold regions. Some deliver water-rich debris inward. Yet the largest compositional sorting has already occurred earlier at temperature boundaries. This late phase mostly mixes and refines. A scale shift arrives in perspective. From close in each collision is a localized event with melt and fragments. From far out it averages into a smooth fading glow belt. The system therefore looks calm when viewed wide. Up close it is still active. The analogy of the heavy stone and gravel remains steady. Large bodies become smoother in their paths as the swarm absorbs irregular motion. The swarm itself thins as it is consumed. Near the end, the belt's brightness appears slightly lower. The clumps appear more spread out. The groove appears more stable. The next transition arrives softly. In that region, the remaining dust will continue to clear. The survivors will keep their orbits with fewer changes. The system will begin to resemble a mature arrangement of planets and belts. A mature system still carries a faint glow of leftover dust. That glow comes from collisions in belts that never fully become planets. In that region, the end of formation is not silence, but a quieter kind of grinding. The scene opens on a wide view where the central star is only implied by the disk's illumination. The main protoplanetary disk has largely faded. In its place, a thinner structure remains. A narrow belt appears as a dim ring of scattered light. It is not as thick as earlier rings. It has a crisp inner edge and a feathered outer edge. The brightness is uneven, with two brighter arcs opposite each other. These arcs suggest that dust is not spread uniformly. The physical details are clear. There is an inner boundary that looks like a fine cut in brightness. There is a soft outer gradient. There are arcs that look like curved brush strokes. A payoff arrives early. The dust in a debris belt is transient. It does not survive long compared with the system's age. It must be replenished. Replenishment occurs when larger bodies collide and release fragments. The belt therefore signals continuing activity even after gas is gone. A simple concept can be named briefly. Collisional cascade is breakup that creates smaller fragments over time. The definition stays short. It is a chain of impacts producing ever finer dust. The language returns to imagery. It is like a stack of dry crackers that slowly crumbles as small taps continue. Large pieces break into medium pieces break into crumbs. The crumbs become a powder that drifts away. The analogy is new and calm. Another payoff arrives in what the powder does. Fine dust interacts strongly with starlight. It can scatter light and feel radiation forces. Some grains are pushed onto more eccentric paths. Some spiral inward under subtle drag from photons. The belt is therefore a source and a sink. It creates dust and then loses it. The belt's brightness is a balance between production and removal. A visual anchor settles in. The two bright arcs are accompanied by a faint dark notch along the ring. The notch is narrow and slightly offset from the brightest arc. It resembles a small bite in the ring. The bite is not empty space. It is a region of reduced dust density. Its edges are sharper than the outer gradient. This suggests dynamical sculpting by a planet. A planet can clear a lane or trap dust into resonant arcs. The physical detail remains gentle. There is a notch with defined boundaries. There are arcs with smooth curvature. There is a gradient in brightness that hints at changing grain density. Another payoff arrives. Planets can shape debris even when they no longer migrate through gas. Resonances and secular perturbations can gather dust into clumps. They can also create gaps. The belt becomes a tracer of invisible architecture. The main analogy of the cracker crumbs remains steady. A planet's gravity is like a patterned vibration through the stack. It makes certain regions crumble more and others less. The pattern is not random. It repeats with orbital rhythm. A number enters with care. Dust grains can survive only thousands of years before being removed by radiation forces and drag. That is like a single night compared with the lifespan of a forest. The comparison is gentle and sets the scale. The belt itself can persist for billions of years, yet its dust must be constantly renewed. This is a scale shift in time that matters. Short-lived grains reveal long-lived structures. A visual anchor appears about 150 words later. The belt is seen edge on. It becomes a thin line with a faint vertical thickness. The midline is brightest. Above and below, a delicate halo fades. The halo is thicker than the earlier protoplanetary disk-settled midplane layer. This thickness signals that debris has higher inclinations. Without gas-damping orbits are more stirred. The belt is therefore puffy in a different way than a gas-rich disk. Its thickness is a physical detail tied to dynamics. The brightness gradient above the midline is a clue to vertical distribution. Another payoff arrives. Debris belts are a late-stage echo of planet formation. They show that many bodies remain on intersecting orbits. Collisions continue. The system continues to evolve slowly. Yet the dominant planets have likely stabilized. The belt becomes a slow clock of erosion. The limit of observation appears and stays specific. A debris belt's brightness does not directly measure the mass of its parent bodies. It measures the cross-sectional area of dust. A small number of recent collisions can temporarily brighten the belt. A quiet belt can hide a large reservoir of unseen bodies. Grain properties also matter. Different compositions scatter light differently. Size distributions can change the belt's color and brightness. Viewing angle can exaggerate arcs and hide gaps. Resolution can blend multiple belts into one. The limit is therefore about interpreting dust as an indirect and time-variable tracer. The belt can be real and stable, yet its brightness can fluctuate. Models require assumptions about collision rates and grain physics. Another payoff arrives in perspective. Even with these limits, debris belts provide a consistent message. Planet formation does not consume all solids. It leaves leftovers arranged into rings and halos. Those leftovers can deliver impacts to planets long after formation ends. They can also feed faint dust that drifts inward and is removed. The system remains a gently active ecosystem of orbits. The analogy of crumbs remains calm. The crumbs are created and swept away repeatedly. The crackers that create them are the unseen parent bodies. The scene eases outward further. The ring becomes a thin circle around a dark center. The arcs remain as soft highlights. The notch remains a subtle gap. The next transition arrives softly. In that region, the final view will step back from mechanics to the full timeline. The sequence from cloud to star to disk to planets will settle into one continuous quiet arc. A system looks settled only because its changes slow to a near whisper. The same physics that built planets continues to shape them through long, gentle adjustments. At this distance, the main story becomes the timeline itself and the way small processes add up. The scene opens far from the star, far enough that the inner planets and belts cannot be seen as objects. Only their imprint remains as faint structure in dust. The debris ring from earlier is now dimmer. Its inner edge is still sharp. Its outer edge is softer and more dispersed. Beyond it, a very faint halo extends outward like a thin veil. The veil is not smooth. It contains subtle streaks as if dust has been stretched along many similar orbits. The physical details remain clear. There is a crisp boundary. There is a feathered edge. There are elongated streaks that hint at orbital shearing. A payoff arrives early. Once planets exist, the system enters a long phase where gravity and collisions continue at lower intensity. The largest bodies mostly keep their places. The smaller bodies are slowly cleared. Dust production decreases. The system transitions from building to maintenance. A simple concept can be named briefly. Secular evolution is slow orbital change from long-term gravitational pulls. The definition stays short. It is gradual shifting of orbits over many cycles. The language returns to imagery. It is like a large clock with hands that move almost imperceptibly. Each tick is small. Over a long interval, the hands end up in new positions. In a planetary system, each orbit is a tick. The accumulated effect can change eccentricities and orientations. The analogy stays unique and calm. Another payoff arrives. Long-term gravitational patterns can move debris into unstable zones. When debris enters those zones, it can collide or be ejected. This creates a slow leak of material. Even after the main formation phase clearing continues, the system keeps simplifying. A visual anchor settles in. A broad dust halo is seen from above with a slight asymmetry. One side looks marginally brighter. The brightness fades into a faint tail that curves gently away. The tail is a stream of small grains placed onto more eccentric orbits by perturbations. As those grains follow their paths, the tail forms a curved smear. Its boundary is diffuse. Its direction is set by orbital geometry rather than by any sudden blast. The physical details are specific. The tail has a curve. Its edge fades gradually. The halo has a gentle gradient in brightness. Another payoff arrives. A planetary system can display structure even when it is quiet. The structure can be a memory of ongoing removal processes. Small grains are generated in belts. They are then redistributed by forces from starlight and by gravitational nudges. Over time, the system develops a faint signature that can persist as long as collisions continue at a low rate. A number enters with care. The system's architecture can remain recognizable for about 4 billion years. That is like the time it takes for a mountain range to rise and erode many times over. The comparison is gentle and sets the deep time scale. This is a scale shift from million-year disk clearing to billion-year stability. The bodies are built quickly in cosmic terms. They then spend far longer in slow evolution. Another visual anchor appears about 150 words later. The debris belt is seen edge on again. It looks thinner than before because dust production has dropped. Yet a faint vertical haze remains. The haze is asymmetric. It is slightly thicker on one side. This can happen if a distant perturber excites inclinations in part of the belt. It can also happen if recent collisions temporarily add a local cloud that is then sheared. The physical detail stays calm. The belt has a defined midline. The haze fades upward in a smooth gradient. A small warp is visible as a subtle bend in the midline. Another payoff arrives in that warp. A warp is a geometric clue. It implies that not all orbits share the same plane. It also implies a long-lived gravitational influence. A single planet can tilt part of a belt over long intervals. The belt therefore becomes a slow tracer of the system's angular momentum distribution. The limit of observation appears and stays specific. At great distances, many different configurations can produce similar faint halos and tails. Grain properties matter. Radiation pressure affects small grains differently depending on size and composition. A tail can be produced by a recent collision cloud, by steady production in a belt, or by a transient resonant sweep. Without time-resolved observations, the origin can be ambiguous. Even with time, resolution changes are slow. The system evolves over thousands to millions of years in these features. That is beyond direct tracking for most systems. Models can bridge the gap, but models depend on assumptions about collision rates and unseen planet masses. The limit is therefore about incomplete information, and about the long timescales that prevent direct witnessing. Another payoff arrives in what remains certain. Whatever the unseen details, the large arc is consistent. Gas-rich disks fade on million-year timescales. Planets and belts persist on billion-year timescales. Dust is a temporary tracer that must be replenished. Replenishment implies collisions. Collisions imply leftover bodies. Leftover bodies imply that formation is never perfectly efficient. A scale shift arrives in spatial perspective. The inner system occupies a tiny fraction of the total halo's radius. The farthest grains can travel tens of times farther than the main belt before they are removed. The system therefore looks larger in dust than in planets. It is a soft aura around a compact architecture. The analogy of the clock remains steady. Each orbit is a tick. Each resonance is a slow adjustment. The overall motion remains gentle. The scene eases into a quieter view. The halo fades toward the background. The tail becomes nearly invisible. The belt remains as a faint ring. The next transition arrives softly. In that region, the final step is a return to the beginning. The process from cold cloud to settled system will be gathered into one calm, continuous line. A star's light can outlast the cloud that once hid it. A planetary system is the slow residue of that cloud shaped into orbits and quiet belts. At this distance, the entire process resolves into a calm sequence of thresholds that repeat across the galaxy. The scene opens on the widest view yet. A dark background holds a sparse field of faint points. In the centre, a single system is only marked by a subtle circular haze. The haze is extremely faint. It is a thin ring and a thinner halo. The inner boundary of the ring is crisp. The outer boundary dissolves into a soft gradient. The halo beyond is asymmetric with a slight taper to one side. The taper looks like a whisper of dust trailing along elongated paths. The physical details remain gentle and precise. There is an edge. There is a fade. There is a slender tail. A payoff arrives early. The same materials that begin as a cold, uneven cloud end as a stable architecture. Gravity gathers. Rotation spreads material into a disk. Collisions build larger bodies. Leftovers remain as belts. The system becomes less luminous in dust yet more organized in mass. A simple concept can be named briefly. Angular momentum is motion stored in rotation and orbit. The definition stays short. It is the tendency for spinning and circling to persist. The language returns to imagery. It is like a long ribbon being twirled. Even when the hand stops, the ribbon's twist keeps its shape for a while. In a cloud that stored motion prevents a straight fall inward. It encourages flattening. It also sets the disk's direction and extent. Another payoff arrives. This single idea explains why disks form at all. Without stored rotational motion, collapse would be more direct. With it, material stalls into orbit. The stall creates time. Time allows cooling. Time allows dust to stick. Time allows the slow ladder from grains to rocks to planetesimals and beyond. A visual anchor settles in. The central region is imagined as a dim circular shadow where dust is absent. Around it, the ring is brightest at a particular radius. That brightness band is narrow and uniform. It resembles a soft bracelet laid on black velvet. The bracelet is not perfectly smooth. A faint waviness appears along its circumference. The waviness suggests clumps that once formed and then dispersed. The physical detail is specific. The band has a defined width. Its inner edge is sharper than its outer edge. Its brightness undulates gently. Another payoff arrives. The disk once held many pressure features, traps and fronts. Most fade when gas leaves, yet the history remains in the distribution of solids that survive. Some regions become planets, some become belts, some become dust that is renewed and then removed. The quiet ring is therefore a memory. It is not a photograph of the past. It is the final arrangement that the past produces. A number enters with care. The transition from gas-rich disk to mostly gas-free debris can occur in about 5 million years. That is like the time it takes for a single mountain chain to rise noticeably in fast geological terms. The comparison is gentle and keeps the scale grounded. The system then persists far longer. That is the calm asymmetry of cosmic time. A brief early phase sets conditions for a long stable phase. Another visual anchor appears about 150 words later. The view shifts inward not by instruments but by imagination. The ring becomes a broad zone where unseen bodies orbit. Within that zone a faint gap appears, then another. These gaps are not empty. They are regions where the dust is thinner. Their edges are sharper than the surrounding gradient. The sharpness implies resonant shepherding or clearing by planets. Between the gaps, the dust is slightly brighter, forming narrow lanes. The lanes look like subtle ridges in a sandbed after a slow tide. The physical detail stays clear. There are grooves, there are ridges, there are soft slopes between them. Another payoff arrives. The system's final look is not a single feature. It is a set of boundaries. Boundaries arise where forces balance. A pressure maximum once held dust. A resonance now gathers or removes it. A temperature front once sorted composition. A collision cascade now produces grains and erases them. Each boundary is a quiet rule made visible. A scale shift arrives in one smooth step. A dust grain is smaller than a seed. A planet is larger than any mountain. Both participate in the same orbital choreography. The grain feels starlight and drifts. The planet feels mostly gravity and holds its path. The belt is the bridge. It contains bodies large enough to collide and small enough to be ground into dust. The limit of observation appears and stays specific. A mature system is inferred more than seen. Dust reveals only a thin skin of the total mass. Planets can be present without obvious dust signatures. Dust can show arcs and gaps that have multiple causes. A tail can come from steady production or from a rare collision. The system's early history cannot be read uniquely from its final pattern. The missing gas phase cannot be replayed directly. Models can propose timelines, yet many timelines fit the same faint ring. The limit is therefore about degeneracy in interpretation and about the long intervals that prevent direct witnessing of the full sequence. Another payoff arrives in what remains reliable despite those limits. The pathway from cloud to disk to planets depends on a small set of tendencies. Gravity gathers, rotation flattens, cooling allows sticking, collisions build and also erode. Over time efficiency is incomplete, leftovers persist, the system ends with both order and residue. That mixture is the signature of formation. The analogy of the ribbon remains steady, the twist persists, it shapes, it then relaxes into a stable pattern. The scene eases outward again. The ring returns to a delicate bracelet in darkness. The halo becomes a faint breath around it. The tail fades into the background. Nothing dramatic happens at the end. The light continues, the orbits continue. The remaining dust continues to appear and disappear in slow cycles. The closing transition is gentle. In that region, the system settles into a long, quiet stability. The sequence has completed its arc. The remaining motion is soft and continuous.